Yeah, then I'll introduce myself. My name is Jong Sub E, but you can welcome to call me Patrick. I usually prefer that name, actually, my English name, because it's sometimes really difficult to just hear, like just catch what people saying. But yeah, just people feel free to call me Patrick. I'm currently in for BTFM as Fang introduced me at Waterloo. My CUDA background is I took a course called Heterogeneous Programming in PostSec last fall. I was in exchange in South Korea. And those two are the pictures. Oh no, just that one picture that I took last year. I'm a big league watcher, so I went to World's Finals last year. Yeah, if you're like a big fan of Faker won it. And also I'm a very good guitar player, so I just put that in there. For your slides, I will give you how to achieve it later, but you will see my cat as well. I did previously qual that Manulife, Geotab, and Board as a full-time, no, yeah, full-time full stack or back-end engineer. But as you can see, I'm here as a CUDA developer, and hopefully I can teach you more about it. And then these are the three things, three mediums that you can reach out to me. You can reach me out to GitHub or LinkedIn or email, like email patrick.xyz. So it should be clear to you. You don't really need to take the picture because, like, yeah, the slides will give it to you at the end of the day. Anyways, workshop prerequisites. Requirements. We're using Google Colab for everything, so you will need a Google account to do copy the notebook to Google Colab and to save it, and then like refer it afterwards. And also, I just want you to have like a strong enthusiasm with the topic, like strong interest to it. It's really nice to know that basic C and C++ knowledge because we'll be going through a lot of memory architecture, memory allocation, memory copies, memory freeze. So that's also one thing. And then I'll talk about more about the computer architecture between the difference between CPU and GPU. So you should better learn like namely like one domain architecture related with CPU and RAM. The agenda is as follows. I'll explain what is CUDA for 5 minutes. I'll talk about GPU paradigm for 5 minutes, programming paradigm for 5 minutes, and CUDA syntax for like 10 minutes or so, and we'll be starting coding CUDA code. And then after that, I'll just tell you what's a future topic, what could be a future topic for you guys, and have a Q&A. And at the end, I want you guys come up to the stage and take a picture of me if you are okay with that. So yeah, and then the volunteers will give out the a stickers, like custom sticker for my workshop at the end of the workshop. So just stay here until you get the stickers. So yeah, what is CUDA? It's a programming language for Nvidia GPUs. CUDA stands for Compute Unified Device Architecture, but it's really used. No one really uses the acronym. Everyone just calls it for CUDA. It's a dialect of C and C++, usually referred as CUDA C and C++. And it can be an accelerator for any parallelizable task. So like it's actually used in machine learning acceleration these days because of the the metrics multiplications are highly parallelizable. That's how it's being used in the machine learning acceleration, and then that's how Nvidia got $3 trillion company. Yeah, namely PyTorch and TensorFlow. And then if you have used TensorFlow before, then you should have seen this code in your PyTorch project. If you want to like run your model or train your model faster, right? Torch device CUDA, and then otherwise, if it's not available, then use CPU. So CUDA and GPU programming paradigm is a little bit different than what's the original CPU programming paradigm. It has its host and device mechanism. So host means CPU and device means GPU. So if I refer as host, it means CPU. If I say device code, then it's gonna be a GPU code for you. It has a name with single instruction multi-threads. I don't really yeah, I put it there so that you just have the idea what's it about, but it's not really it's a little outside the topic of the like workshop, so you don't really remember it. But it's nice to have, and then this is the Lens taxonomy about like what's being done inside of a CPU, like how you run the data and also like run multiple instruction at the same time. But I'll say the SIMT is in between SIMD and MIMD, but you don't really have to know about this. Anyways. The programming concept is like programming structure is as follows. You have to first allocate memory to CPU and GPU to run the thing, to actually like run the program. And then you need to copy data from CPU to GPU because GPU has its own memory, like GPU memory. You will probably know it as GDDR5 or HBM. And then now, as the data is loaded to GPU, so you can actually load the GPU program to GPU cores and execute it. And then you will have the results. So yeah, and then to use that result back to you and show it to your screen, it has to come back from the GPU to CPU. So you have to copy data from GPU to CPU, and also like to prevent leaking. You have to also read the memory. This is a slide that I got from like during my course. I put the source at the bottom. Yeah, you will have the slides at the end. So, but it's okay. So the processing flow side, yeah, this is just what I just said. First, you allocate memory. I just took that out. Bring the memory. That's also easy. So just copy data from the CPU memory to GPU DRAM. And then after that, you just load the program to the CUDA cores up there. That's the GPU cores, and then run, and yeah, and then you will have the result back on GPU DRAM, and then you have to copy back to CPU memory so that you're able to use the result from what's been done in GPU. GPU architecture. There's like bunch of terminologies that I want to go over with. Kernels, if I say GPU kernels, then it's just a function in GPU. So if I say kernel, right now for this workshop, then just think it as like a function that runs under the GPU. There's CUDA cores in the GPU, which is just the hardware. Like it's just a CPU core. It's like more of a CPU core instead of the GPU, but we will have a lot of them. Wars. It's also a hardware concept. So if you gather around like 32 or 64 cores of CUDA cores in a chip, then it's called warp. Warp. It's also a little outside of the workshop thing, but warps shares their program counter. So it actually runs the same instructions within for a core in a work. And string multiprocessor is just a gathers of words. So usually there's 4 words in one SM. I'll show that. I have a diagram later on, so don't worry about it if you don't understand the concept right now. And then we go on to the threads. Threads is a CPU. No, sorry, it's not CPU. It's a software concept, which is one-to-one, like somewhat one-to-one concept, like matching corresponding concept with CUDA cores. Thread block is also a software concept. You gather a whole bunch of threads, and then you think it as like a whole block running at the same time with you, and that's called thread block. And then there's grid. If you have multiple thread blocks, then you will have the grid. That's the software concept here. And then there are the kernel wizard keywords. I just said that kernel is just GPU function. So these wizard keywords are used for GPU functions. And then there's like 4 of them, but we'll be using only global, so just don't worry about the other. They're like that's for the outside of the course, so that's fine. Just you will be using global today. Yeah, this is a diagram that actually shows you with the difference with the thread and then CUDA core. So you can see that thread and drag block and grid are all the software concepts, and also CUDA core, SM, and device are all the hardware. And then the Nvidia compiler will bridge between the software concept and the hardware concept, and then you don't really need to worry about what's going on within the hardware, but later on you need to know, but not anymore. Actually, I brought this diagram from Nvidia white paper. So this is the A100 streaming multiprocessor, and then that's the Hopper 100 streaming processor. So as you can see that there's a whole bunch of cores inside one SMs, and then there's like 4 sections, right? You can actually see there's like one section there, one section there, one section there, one section there, right? That's actually a warp. That's the warp. So that's the warp concept here. So one streaming processor contains 4 warps, as you can see at the white paper here. And then within the warp, as you can see, this is 16 in 32 cores inside. It has like 32. No, there's like 8 floating point 64-bit cores there, tensor core there. And then when it comes to Hopper architecture, the number doubles. So you have 16 in 32 CUDA cores, and then there's there's like 32 right now for the floating point 32 cores, and also for 64 there's 16. And then there's a tensor core for matrix multiplication, but that's not really needed. And then this is the whole GPU. So this is the one SM that goes into the GPU, but this is the whole one chip, that everything that goes into one chip. So right now this is Hopper 100 full GPU with 144 SM. So this streaming multiprocessor, that one thing, like 144 of them goes into the thing. That's how this GPU is highly parallelizable in some sense, that having many cores within a single device. So let's move on to the CUDA syntax. Kernel definition, I said kernel is always a GPU function. Kernel definition starts with the global keyword. So I did tell you that before. There is 4 kernel keyword. We only using global. Don't worry about the others. But right now, yeah, we are using global keyword at the top, at the start of the function definition. And then usually the return type of kernels are void. We don't use any return types in CUDA kernels, usually, most of the time, pretty much 99%. So to return a result from a GPU kernel to CPU, we need to put in another parameter, like return parameter, within the function. So right now we have parameter 1, parameter 2, and then return parameter for as a floating point pointer. And these floating point pointers should reside in GPU memory, not CPU memory. CPU memory you will allocate, that's why you allocate with the malloc, memcopy. That's why you have learned in your original C course, but we were using some CUDA functions to actually set a section for GPU, and then set a memory allocation to GPU, and then copy data from there. And then we define the function, so we have to execute the GPU function so that it runs and we get the data. This is run on the host side. So as you can see, I put into main deliberately so that it actually runs on CPU code. It's the host code that you already know. And then I named it the function as test kernel, and you see that test kernel is right there. I'll probably talk about that 3 bracket block later on when we actually do touch the code. But as you can see, that's there are 2 parameters in between. That's the CUDA syntax. And then first one will be the number of the blocks that we be assigning to the kernel. And then the second parameter will be the block size that we be allocating, like the number of CUDA cores or threads that we allocating within a block. And these parameter I just said that they should reside in GPU memory. So we'll be using these functions like CUDA malloc, CUDA memcpi, CUDA free. I'll talk about the usage and when we actually do code. And then the other one is you see that there is a function named CUDA device synchronize. That's actually it needs to be there because GPU kernel code is always asynchronous to the CPU code. So you have to always sync with the code with the CPU so that you get the result. I will have an example when we actually do code. Actually, you know what? We need to code. It's fun to code. I tell you everything that I need to do, like for the software side. Okay. I didn't give you this slide. So if you go into the hack pack that I sent you guys, or you can see it in the schedule, if you see workshop specific resources, there's a workshop repository. So, and you will just click the link and you'll be in my repository. If you want to store it, definitely store it. Thank you. And then you can click on the notebook.iompy, click on it. And then on the top, you will see that you will see that this opening Colab button. So click on that too. So if you open it right now, you will see something similar to this. Did everyone get that? Or did it help? Okay, give me a thumbs up if you're good. All right, I'll move on. And then there's a setup part of it, but before doing that, you should be copying this notebook to drive before you start anything else. Yeah, you can say that, but yeah, open it on your tab, and then once it's copied, then it's gonna be in your local drive, and then it will be automatically saved so that you actually go back and then report back it to after the workshop as well. And then we will start setup now on. Did anyone have trouble with copying the notebook? Oh yeah, just go to the hack pack, and then if you scroll down on the second page, there's like workshop specific resource. Click on the link right there, the workshop link. That's the workshop repository link right there. Yeah, you see that, and then afterwards you will go into my repository here. Yeah, click on the notebook.iombpy, this one, third file. And then there's like a button over the top on the top, viewing Colab. Yeah, you should click that and it should redirect you to Colab. And then you will see this one, and then you should copy to drive. All right, I went to twice, so everyone should be fine. Yeah, and then I wrote everything down. So what you need to do is just click runtime, change runtime type, and then T4 GPU, make sure T4 GPU is selected, press save, and just connect. Press connect on T4, make sure this is T4, not CPU or whatever. Connect, and then take some time. Yeah, once it's connected, you will see that RAM and disk is right there. And just run these top 3. That's for the checking actually whether things are working. So yeah, you should get something similar to this. The order doesn't really matter. As long as you get like hello from block block 0, 1, or whatever, like for output, you're good. Don't worry about the order, anything. That's fine. Did anyone got stuck? Is everyone good? Give me some signs. You're doing great. Okay, good. Afterwards, yeah, first, hello world, actually, right? Hello world. All right, let's just, is it still visible? I think it's like little, my codes are too long to actually put it in one line page. Your first CUDA code, what's the difference between CPU and GPU code? Right now, this function is gonna be your CUDA code, and then that's gonna be your first CUDA code running on GPU. And it will just print out hello world from GPU. But try to run it right now as is. Like, don't touch anything, just try to run it right now. And then it will say that a host function call could not be configured. Do you get, does everyone get this error? Yes, okay. So what's missing right now? We don't have the global syntax trigger of CUDA. So let's add that right there. And then let's run it again. Now you see that hello world and hello from world from GPU is actually there, right? Give yourself a clap, like you just did write your first CUDA code, right? The thing is, but I did actually like have a comment right there, but try commenting this out, this line out, and then run it again. Do you see hello world from GPU? Do you see? I did say that before coming to this code, I did say that the GPU function kernel is always asynchronous to the CPU. So therefore, if you don't put in this function right after the kernel, it will not show up the result. You will not be able to access the function result, even though it has run. This function, this actually has run on the CPU side, but it actually exited. The CPU has exited the program before GPU was able to like put something output to it. That's what it actually did. So that's why you need to put this CUDA device synchronize every single time. Make sure that you have this function every single time you run a GPU kernel. Great. Yeah. And then run it again. See, it's working again. So let's move on. We'll be doing vector addition for the whole like rest of the workshop. So we'll be starting with the single integer addition. So we're just doing like 3 plus 5 or something like that. And and then remember the flow that I told you in the slides. First, allocate memory to GPU, copy GPU to CPU, you run the kernel GPU function, and then you copy back from GPU to CPU and free memory. That's why you need to do every single time you run the GPU kernel. So, and then there's like 3 keywords. Those are the ones that we'll be using to allocate memory on GPU and so on. So that's the kernel that we working on. Very simple. Just takes 3 integer characters, and then pointer characters, and then just dereferences, and then ask, and then take the result to C. That's simple. Simple enough. Put a kernel. We have the global, so we don't really need to do anything for that. And then let's go into the main. We have A, B, and C. We want to add A and B. So we want the C result of this function or this whole cell to be 5. But let's run it right now and then see the result. Right now we get 0 because we haven't done anything, right? We didn't do anything. So we are checking that is actually getting things that we are actually need to do. Or we can change like C to 2 and then run it again. And then we get 2. So it's actually taking the output is actually taking the C, right? Okay. So what you need to do is first allocate the memory So let's start from here. I gave you an example for DA. Oh yeah, before going on to that, sorry. So we need device pointers. So actually, there's like nothing much of a syntax trigger. It's all the same. Like it looks the same as regular CPU pointers, but I just put D underscore so that it's so have a meaning that it's a actually device pointer instead of a CPU pointer. But the declaration itself is pretty much the same. So we need to allocate memory to these device pointers, right? So what we're gonna use is this function could void could malloc, and then it takes the device pointer which gonna be typed as void double pointer, and then we will give the size of how much we're gonna allocate memory to GPU, and then we are just doing single integer, so there's a size parameter as well, which is just a size of the integer, and then I have an example there, and we need to do that for the same for both all of DA, DB, and DC. So let's do that. DB size. Sorry, I did something stupid. Yes. Is everything done? Yeah, that should be not done. And then second part of the flow was copying CPU data to GPU. So we'll be using CUDA memcpi. This is the function signature. So we will have destination pointer, which gonna be our device pointer, which because we're copying from CPU to GPU. So that's this first parameter has to be the destination, so we're copying data to GPU, so we're using GPU here. And then A is the source pointer, which is going to be A. And then we'll be copying int 4 bytes, so we're using the size there, right there, up there. And then this is a enum for we use from MCPI, so that to tell the function that we are actually copying host to device. So CPU to GPU. So right now it's using the terminology of host and device. So host always means CPU, device always means GPU. So I have an example here. So just comment that out, and then you need to do that for CPI for only for DB because we're gonna have the result in this in C later on. So we don't really need to worry about that. No, DB, sorry. Size, CUDA, mem CPI, host to device, right? And then we'll be launching the kernel. We're launching the kernel. Just comment these two out. Yeah, right now. We will write our own definition there later on, but just comment these out. And this function was named add, so we just have add that there, and then 1 Let's leave that for now. I'll talk about it later. And then we just put in device pointer A, device pointer C, device pointer C, and then we just run it. And then every single time I tell you when we run a GPU kernel, you should always run CUDA device synchronous to actually have the result back. So we supposed to have we haven't run it yet because we have to put it back to see the result back to GPU, but we are 100% sure, pretty much sure that this function has been run on GPU, and then we will have the result. So we need to copy from device to host. So we will use memcpi again, but what's the difference in this code is that the source pointer is different. No, the destination pointer is different because we are copying to CPU pointer now. So we are using the NC so that we are copying to the CPU pointer. And then we are gonna have device C that we are copying from the device pointer and size. And the last part is actually CUDA mem CPI device to host, not host to device as the first one up top. So just make sure that you have device to host right there. And then, yeah, you need to clean the memory, right? So I have the CUDA free function there. You just put the device pointer that you wanna free for. We have allocated that the CUDA free db db and CUDA free dc there, and then we haven't finished everything, so let's run it again. Yeah, 5, right? We got the correct value. That's how it's run. It has run it actually run the GPU kernel, and then it did add 3 and 2, and we just set the 2, but you can change the numbers like if you like let's say 200, and then it's gonna be the result should be 203, right? And then it's just right there 203. So you actually run the GPU kernel. You are able to allocate memory now. You're able to free the memory. You can copy GPU to host back to GPU. Now you learn all that, and then that's like 80% of like what you did today. What?
I ran and I got a 3 instead.
Okay. What you're missing? Probably you're missing. Are you missing this end right here? That's the pointer. You need to check that whether it's a pointer or not. That's what I did. Like,
okay. It is a pointer. It's a pointer.
Yeah, it's a pointer. Okay. You come back to me later. You can move on. I don't really have much time. And then move on. I said that there also are software stuff called thread blocks and grids. We will be using that right now, starting now on, and then we'll be doing vector addition to actually to learn what's thread block, what's thread block and threads and grid. Yeah, we'll be using grid. Same thing. Let's skip the. Okay, I'll explain a little bit. So we'll be using the 16 length of 16 of array that we've been doing, and then there's like a function I made up for to just put random numbers into to each vector so that we can verify the results. Let's skip the kernel first. Let's do the what you need to do on the host side. So always we need to do allocate. So yeah, we have the data that we want to like add A and B. That's the now it's A and B are pointers now because they're vectors arrays, and we allocated the size of n, which is 16. So size of n, so 64 bytes, and we just set them as a random in, and then for the last one, we just for C, it's our return pointer, so we just set it as 0, and so that we can verify that our results are 0. Actually, let's run the cell. It should run. And then you see that the A and B there, like I added the index right there as well, so that for a reference, as you can see, all the like things are working as expected. Right now, we are doing anything on the GPU side. We have the A and B there, and then the results are not yet updated. So let's start what we need to do. We need to always allocate memory to GPU. So what was the thing again? Was CUDA, malloc. All right, if you forgot, like me, I don't have like good memory, so always go back and then check like whether like you have the thing, and as always like check the actually you're doing using the correct type. This is always double pointer, so void double pointer, and then you have to do the A, and you're allocating size, right? That, and then you do the same thing for B and C. right? That's the memory allocation that you need to do. Is everyone good with that part? Give me a hands up. Very good. Okay. And of course, we have to copy the memory from A to DB and B to DA. So CUDA, memcpy, and if you did forget, then just copy here, and then press copy that there. I did this thing, and then I made a big mistake when you have to. So A is pointer now. It's a vector. So last time, like I did with walkthroughs, I did mistake here. Don't forget to remove the and sign in front of A if you're copying from up, and also and same thing for B. And you get the sites. And this is something that I want you to do if you want to like make sure that actually it's like working, but it doesn't really require, so I'll just like skip it. You can do memset on C if you like. Issue at the moment. So now we need to launch the kernel. Yeah, what we need to do was add 3 brackets, and then we need to do DA, DB, and DC. That's what you need to do. And then I'll put this in. No, I didn't need to do that. So n, as the comment says, n needs to be placed on the left side of the brackets. That means we are gonna be using blocks instead of threads and stuff. So thread block is a block. It's a block of that we actually group them together. And then in each block, we are putting 1 threads each. So we're gonna have a 16 block with 1 thread each, and then a thread block would go into a and actually it's a thread actually that goes into the array. But I'll get back to that to when we actually do touch the function kernel. But have that there right now, and then always when you call the GPU kernel, then always CUDA device synchronize you need to do. All right. So yeah, and then let's say we don't really have running yet, but let's say it's already there, so we have to copy the device pointer back to here. So CUDA memcpy to C from DC size and CUDA mem, and then this has to be device to host. Then we're gonna print the result. That's just the code, like for loop, simple for loop. And of course, after copying that, you need to free the memory. So just CUDA free DA, DB, and DC. So the host code part is actually done. We will go back up to the top, and then we will work on the kernel. So now, what's missing? Like right now, the kernel is actually missing something. It's actually missing this global with that, right? Because all the CUDA functions has to have this global underscore global and underscore so that it to notify the compiler that it's actually a GPU kernel. Actually, we are using the, thread blocks. So we are introducing a new keyword for CUDA. It's called block IDX. It means the index of each thread block. So we are using 16 thread blocks for 16 long arrays. So right now, and then each one will just add to each other. So we just can use use the this block IDX X is block IDX. Be aware of this has to be capital block IDX X and block IDX X. That's what you need to do. Is everything clear up to here? Any questions? It's good. Give me a thumbs up if you're good, or not. Okay. As you can see, there is an X, a X parameter in front of block IDX. So if you can assume that they're gonna be Y and Z later on, but I'll talk to you about that later. Let's run the code. Actually, it should run. Do you get the results? Like correct results now? Actually, you do, right? We actually have 16 length of array, and we are accessing this A and B, copied it, copy from A and B and save it to device, and then GPU actually access divide this block in each IDX index goes to 1 to 1 to 16 or 0 to 15 if you're like using right now it's 0 to 15, but you understand. So therefore, now you can use the thread blocks now, and then next we'll be using threads. So in a thread block, actually there can be multiple threads. So, and then the second parameter of the CUDA, what we see here is the number of threads. I actually said that in the slides, but that's the number of the threads in each thread block. So it's pretty much the same thing, but we'll be using the it's pretty much the same thing as previous example. So let's go through quickly for host memory, allocating memory, and again, yeah, same thing, CUDA, malloc. And then if you're too lazy to do this, then just copy, like everything is the same. Just one thing that is that the function call and these something in the kernel itself. So let's just do copy and paste. And then you need to like copy the results back to CPU. So you do, and then you have to free the GPU memories to prevent leak, right? That's not where it's supposed to be. That's there, and then yeah, come up here when you added the CUDA kernel calls. Now we replace with 1 to n. Now we're gonna have only one thread block, but there inside that thread block we'll be having 16 threads within that thread block now. So if we go up to the top, now there's another preserved keyword called thread IDX. That's for the index for each thread block. For each CUDA core where a thread are assigned to. So now you can use thread IDX.x in this line and try that. Thread IDX.x, thread IDX.x, thread IDX.x. And if you run it, yeah, always. Yeah, I'm done. You have to put that there, global void, and add that there. Yeah, I forgot that. Sorry about that. But as you can see, the compiler can tell you that it's not actually configured well, so I just like figure that out. And then you can run it again. Now the results are actually correct.
Scrolling up where you were writing code about the thread.
Yes, here.
Okay.
Yeah, it's just you can use this thread IDX for this section. So you can use thread IDX and for everything here for indexing. So this function is actually called in each CUDA cores, just that they have each CUDA core has different thread IDX index for each thread, and that therefore it can access the correct array index for the A, B, and C. Therefore, it can actually give you the correct result, even though it was all random, right?
Yeah, it's like threads go up into blocks go up into stream only.
So there's like two things. So block is just a group of threads inside, and then you can have multiple threads. Thread blocks, actually. Oh, no, sorry about that. Yeah, you can have multiple thread blocks, and then there can be a number of threads inside in each thread block, so that there's like multiple of them. There's a number that usually we go for, like in each the number of threads that we do for each thread block, but I have a code that you can actually experiment later on. So we get to that right. Oh, actually, going way slower than that. I thought like it's almost 50. So right now we've been using the same number of threads or thread blocks as the array length. But actually the array length can be arbitrary, right? It can be like 100 or 100, 111, 112, or whatever you name it. But right now we've been using the same number, like pretty much. Or at the moment. What is this? Oh yeah, I didn't use that. Anyways, same thing, pretty much. Yeah, I should have just done it here. Yeah, copy paste again. Wait a minute. Paste again. And should work for this as well. Launch kernel. Oh yeah, I have the launch kernel there as commented out. Yeah, there's something that I need to show you there. 3. Oh. Oh, okay, I forgot. Are you guys on 2.4 or 2.5? I'm sorry. Yeah, I missed one cell. Are you guys on 2.4? Okay, actually, so yeah, actually you asked a good question. Like you can combine those two thread blocks and thread within the thread, and then I showed it in the slide as like it's called grid. So we'll be using grid this time. Pretty much the same thing, but like just copy and paste everything. Just one difference is the number of thread blocks that we'll be using both parameters inside of the brackets now. And remove that. And then there's one more keyword that we need to use to actually run the code. Give me a moment. I need to copy this one off to here. Then you should comment that out. I explain more about this. Right now, it's actually I set it as so that it's actually perfectly divisible in terms of like integer division. We are using 32 length of array vector, and then we are using the block size of 16. So there are gonna be two thread thread block, and then within one thread block, there are going to be 16 threads. And then, as you can see here, we just divide n with the block size, and then that's like 32 divided by 16. That's going to be 2, and we're going to have 2 number of blocks and 16 threads in each thread block. So therefore, we're going to have 16, and we now need to do kernel. So don't forget, you need to add global there, and you have to comment these 2 out. Now we need to use block dim. That's the dimension of CUDA kernel that you need to use in each thread block. So that's the dimension of the length of each thread block. Therefore, what you need to do for this IDX is thread block IDX multiplied by X block. You have to multiply by dimension of it up. And then you have to add now you're in your thread block you're assigned to because you multiplied the index and the dimension, so you're just skipping, and then if you add thread idx.x there, then you're now in the correct step of where you're adding your vectors are. Is that understandable? Yeah, it gets tricky from here.
Can you say block dimension? Do you mean like the number of threads in the block?
Yeah, block dimension. Yeah, it means the number of the threads in each block. So we have set this as 16 right here, block size, right? So that's it's gonna give you 16. This block name.x will give you 16. Okay, we can run the code. And then as expected, it's gonna be run smoothly. Sorry about being over time, so I have to give you remainder as somewhat homework. I'll give you an idea about what you need to do for other 2, and the 2.8 is I want you if you're more interested, then I'll just take a challenge of this and then submit a PR to my repo back in the repo, and then I can review for you. But I'll give you a little bit of ideas what you can do for each ones. So now on, I did talk about the arbitrary length. So now we've been using the array lengths that are perfectly divisible to the block size. But now we can have multiple lengths of arrays, and then it can be 50, 51, which are not divisible by the block size. And that's pretty much the same thing. But the one thing that you need to do here is that you need to check now whether you're going over in terms of getting the index of a thread, because you will have some leftover threads when it's not perfectly divisible for each thread block. Then therefore you have to check before that whether a thread is not accessing the memory that it is not supposed to do. Otherwise, it's a segmentation fault. So that's a idea right there. And then I'll just want you to figure out what you need to put in there, and then why is this parameter length is in there as well. That's what the idea of this is. And then we actually expanded everything into a matrix addition. So now we can use, I did talk about this. You can now, there's X and Y and Z that you can actually use to allocate as coordinates for your GPU kernels. So now you can do 2D operations. That's one example. And then I have seven defined 7 by 7 matrix, and then you have 4 by 4 block size, which is not perfectly divisible. I deliberately put it in that way so that you have to go through, check the length and stuff. There, pretty much the same thing, just allocate, copy, run, put it back, and read. Yeah, probably I would. Okay, just run this code. I'll explain that later. It takes a little bit of time, so I'll just go through about some other stuff that I wanted to go over. Just run it, and then let's go back to the slides a little bit. So what's next? What can you do? Like this is just the beginner. It's very introductory workshop. I didn't have to go. I wanted to go through all of these things, but like they didn't really have much time for me to go through. So shared memory, and there's like memory quality, there's like memory architecture you can go through. Then also there are parallel algorithms for only for GPUs, which can be reduction, like spare matrix and vector multiplication, and then convolution networks that you can work with. And there's like other results. You can use white papers, and then there's a book called Programming Massively Parallel Processors. And then also, I gave you an answer. So this slide and the all the answers for the cells will be in the answer branch. So let's go back to the here and then you see answer branch. So you'll have all the codes, all the answers here. So don't worry about if you don't get it. Like you can always refer back to this answer, and then there's slides. It just took the took my picture out. That's it. All the contents are the same. So you have that. And let's go back to this. Go back to the notebook, and then it should have run. So as you can see, GPU is much faster here, computation wise, but benchmark. But GPU time taken is actually pretty much similar because of the overhead of memory allocation and bring the memory. That's where the all the overheads come from. The actual computation just takes way faster than the CPU. And then when it comes to my desktop, actually I'll show you. I have to run it, but actually CPU is much faster than GPU. Well, the computation itself is faster on GPU, but the getting the result back to CPU is actually much slower than CPU, just doing computation on CPU because okay, never mind. I'll if you're interested, come back to me later on. I'll show it to you, but